So, it seems like some of us are a little stuck on getting this standard form. Remember, I just need an idea. It doesn't have to necessarily be the right one. I'm going to write this problem up here first before I stop the poll. We have 2x minus 1 times x minus 1. First off, which form of the polynomial do we have right here? Factored form? How do you know it's factored form, Cantor?
I wanted to say.
Okay, so remember, this is what we need to work on. It's never just, oh, it is this thing. Like, there's a reason why you're saying that. Can anyone add on to Kaya?
Is it because it's two linear factors kind of put together but not put together?
Okay, so let me ask you this. Would this be factored form?
Yes. No.
Not really?
They've got a multiply.
Oh yeah, what do we have to do with factors?
Multiply.
We have to multiply them, right? So it's factored form because we are multiplying factors. Now, do the factors have to be linear?
No.
Right? So they don't have to be linear, but the factors do have to be multiplied. And heck, it doesn't even have to be binomials. Binomial meaning two terms. X squared minus 3x plus 4 times x minus 5. Is that still two factors? Right. These are still factored forms. Okay? And so we want to recognize that, hey, I have factored form. I want to get standard form. Now, really quickly, two things I want to point out because this is something that showed up on the last understanding check. What type of function, even before I get the standard form, what type of function is what we started with?
Quadratic.
Why do you say quadratic?
Because there's two x's.
Okay, because there's two x's. So then what type of function would this one be?
Cubic.
But there's only two x's.
No, x squared is, that is basically two x's.
Okay, so we need to work on the language a little bit. Can anyone add on to or clarify this statement about why this would be quadratic?
Degree 2.
Okay, Gabby? Because it's what? Okay, because it's degree 2. How do we know it's degree 2 though? There's an important detail that we're missing here. Okay, the x's are being multiplied. Okay, and so when we multiply x times x would give us x squared, so that would be degree 2, but there's something else that is fundamental to this.
Multiplicity.
Closer, you get into another detail. And please hear me very clearly on this. When I say there's something else, I'm not saying that the whole idea about the degree is wrong. I just want us to recognize there's another detail. Salita, you involved in this? Engaged in this conversation? Come on, pick your head up. Get engaged. All right, multiplicity adds onto it. Gabby, it looks like you were about to say something. What's up? You sure?
Doesn't it have something to do with the exponent being like?
That's the idea. That's a big part of it being degree 2, right? Remember, the degree is the highest power, right? Okay, highest exponent. But there's something else that is fundamental to this idea.
What are the two roots?
Say that louder.
Two roots.
How many roots would this function have?
1.
1. This would also have
1.
1, which is how many roots? 2. And again, there is something that is fundamental to this.
Theorem of algebra.
There we go. What is the fundamental theorem of algebra? This is critical to this unit and literally algebra in general. What are you saying?
States that a degree in polynomial has counted with multiplicity exactly and zeros.
Okay, that's literally the definition. But an nth degree polynomial, right, the degree being the highest power, an nth degree polynomial has exactly, when counting multiplicity, n roots, right? So if it has 2 roots, it has to have what degree?
2.
Second degree, meaning it's quadratic. Okay? You good with that idea? So then what type of function is this one right here? cubic, because this has how many roots?
Two.
2, and this has
One.
1. So it has 3 roots for what degree? Third degree, so it is cubic. Right, it's not enough to just say, hey, I'm counting the x's, that's my point. Again, this is something, by the way, if you missed Friday, we went over the last understanding check and we spent a lot of time on a bell ringer about this. We talked about the idea that you have to pay attention to the number of roots. The number of roots is what tells us everything here. And so that is very, very, very important, the idea of the fundamental theorem of algebra. Whew. All right, all that to say, 2x minus 1 times x minus 1. That is factored form. We wanted standard form. Can someone tell us how to get there?
The point.
Distribute.
Distribute. First off, distribute. Punnett square is something specific to biology, but I understand what you're saying there. It's called an area model, but there's 2 different options. Plainly put. Activity 4.3, especially if you were gone when Ms. Estel taught this or went over these ideas, this is a small part of the understanding check today. Pay attention, it is super straightforward. There are 2 methods. We don't FOIL because foiling does not work every time. Specifically, this is when FOIL starts to break down. Foiling only works when you have 2 terms multiplied by 2 terms. Anything else, can't do it. You can still distribute in this case. You can still use the area model in this case. So practice using mathematical language and mathematical concepts that will always work. Okay, so 2x times what?
X.
And what is 2x times x?
2x
squared.
Right? Literally multiply the coefficients. 2 times 1 is 2, and x times x is x squared. That's it. Okay. 2x times negative 1.
Negative 2x.
What are your questions up to this point? Alright, what do I need to do still?
Distribute the minus 1.
Distribute the minus 1. So minus
X.
There's 1.
right, negative 1 times negative 1 is plus 1. You always want to simplify if at all possible. Is there anything I can simplify?
2 negative 2x and negative.
I have negative 2x's, I'm subtracting 1 more x, so I have a total of so that's the distributive the distributive method. Hudson already referred to the Punnett squares, which is called an area model. This is a model that I actually really do like and recommend because it helps you organize your thoughts. In this top left corner, you always put the operation that you're doing. What are we doing between these 2 binomials? So I would put multiplication here to indicate that I'm multiplying. And then I put my factors, 2x and negative 1, and x and negative 1. Wasn't our first step here just 2x times x? What's 2x times x? And then we did 2x times negative 1. What's 2x times negative 1? And remember, the operation that we're using is here to show what we're doing between these terms. And then negative 1 times x is negative x. Negative 1 times negative 1 is positive 1. I like to circle my like terms like this and show them added together off to the side, but then we get 2x squared minus 3x plus 1. Same answer? So does it matter which method you use? All you have to recognize is that you have to multiply those binomials. It's your choice of how you do it. Questions, comments, or concerns? Easier than we made it? Hopefully. Please note this is something we did last unit as well. We talked about if we have factored form, we would just multiply to get standard form. That's all it is. But please note, I'm not going to say, hey, multiply these 2. I'm saying, hey, we have factored form, I want standard form. That implication immediately is to multiply. Elijah, you good with that?
No,
What are you not good with?
I didn't just see learn it.
Huh? You what?
I didn't see none of it.
Why not?
I can't see. That's why I been sitting up there.
Then why didn't you talk to your group and have them sit up here with
Because
you?
I don't want to sit up there.
Well, let's move up here then. It's better to be close to the board. Emma, Brantley,
What's wrong?
and Alasia, let's move up here.
They don't got to move up there.
Nope, all of us are moving together. We are a small group, we work together to help each other grow and learn. Okay, from there, quick little recap before we do a little bit more practice before the understanding check. So we're looking at what's called the zeros to hero, connecting the idea of those roots and those factors, all those fun things. So one thing I want to remind you about is from this getting started, it is on page something.
M1-168.
168, thank you. Yeah, M1-168. So we want to recognize the degree of the function, right? First degree here, both of these are second degree, both of these are third degree. But the major thing to remember is we also talked about the idea of multiplicities here. You have multiplicity when that root what? When it repeats. It's literally a multiple, right? So if I'm looking at these roots, what are my roots? X equals
0.
and x equals, okay? What are your questions about those two roots? About how I got them? All right, that means we understand it completely. Cool. So there's our two roots. And what are their multiplicities? They're both a multiplicity of 1. Notice those factors only show up once. Whereas if I look at this one here, what's my roots?
X equals 1.
X equals 1, but it's the same for both of those. So it's x equals 1 with a multiplicity. Just meaning it happens twice. Yes, ma'am?
Could we write the exponent of what is in Alright, so you know how for the problem we're doing is x minus 1. Could we write outside of the parentheses a 2 to show that there are 2 of them?
So like, just rewrite this as x minus 1 squared?
Yes.
Yeah, you can rewrite it like that. It's equivalent. Yes, okay. And that also clearly shows, hey, right, when I set this equal to 0 to find my root, and I set 0 equal to x minus 1, add that 1, right? X is equal to 1, but I had 2 of them, so it'd be a multiplicity of 2. Yeah. I will point this out, and this is an important thing to recognize. On the graph, when there's a multiplicity of 2, what's going to happen at that 0?
It's going to bounce off.
It's going to bounce off. Remember, when it's an even multiplicity, it's going to touch that x-axis and then bounce off of it. So keep that in mind. All right, so multiplicities, quickly reviewed. So don't forget, one of the things with graphing, where does the function, the dilated function, change from positives to negatives?
When they intersect the x-axis.
Okay, so what are those called? The
0.
zeros, or also
X-intercept.
x-intercepts. The one reason why I specify x-intercepts is because, remember, zeros can be real or imaginary, right? Which of those are you not going to see on the x-axis? Imaginary, right? You're not going to see those imaginary on the x-axis. So it's not all zeros where it changes from positive to negative. It's only the x-intercepts, right? So if you ever get imaginary ones, you're not going to see them. All right. So notice how I identified my 0 here. And if I take a positive and I multiply it by a negative, what do I get? Negative. So the dilated function here will be negative. And then if I look at this region, the polynomial is going to be positive. Is it going to continue going positive for forever?
No.
No? What's it going to do?
Go back down to 0.
Go back down to 0, right? If it's positive, but it needs to get down to the 0, it's got to hit a, what is this point up here called? A maximum, right? It's got to hit a maximum to come back down to that 0. And then I look at this region, and a positive times a negative is negative. Good. Right? That's all it is, paying attention to those regions to determine where it's positive and negative. One thing I will point out, if you want greater accuracy, all you have to do is actually substitute values in, right? So I went to that x equals -1 here. L of -1 is 10.5. I just substituted that into the equation. H of -1 is -1. And so remember, I'm literally multiplying. So when x is -1, the y value is like -10.5, somewhere down. Oh no, right here. And then I looked at L of 2 and H of 2. If I multiply 4.5 times 2, it's actually a 9. And then similar thing over here, get -7.5. You don't have to do this. This is just something that will give you a higher level of accuracy, getting a few points in there. Remember, I'm not looking for super accurate. I'm looking for you to recognize where it's positive and negative to sketch it out. But you can get actual values to make it a more accurate graph. Alright, but this is where we are, that idea of multiplying. One thing I do want to emphasize and point out to you here is this. How many factors does this function have? It has 3 of them, right? They're all linear. Oh yeah, this page 1 something, 76, right? There are 3 linear factors here. So it has how many roots? 3 roots. So it's what type of function? Cubic. Okay. And so we even see that in the standard form. But I want to point out, how many factors can you multiply at a time?
2.
Only 2. Please pay attention to that detail. We're about to look at a problem with that before we do the understanding check. But you can only multiply 2 factors at a time. That is a key thing here. People try to do more than that and it messes them up because you can't. And this should make sense when you just look at numbers. 2 times 3 times 5. How could I multiply these 3 numbers?
From left to right.
Okay, so I could go from left to right. So I would start with 2 times 3, which is
6.
times 5, which is.
30.
Notice how many did I multiply at a time?
2.
Just 2. Right? Could I go from right to left? What's 5 times 3?
15.
And then I have 2 times 15, which is?
30.
Could I multiply 2 times 5 first?
Yeah.
2 times 5 is
10.
10 times 3 is?
30.
Notice, does the order matter? Not at all. It does not matter what order you multiply them in. The only thing that matters is you can only multiply 2 factors at a time. Questions, comments, or concerns before we do one practice problem? All right, you're going to work on this in your small groups. One thing I want to emphasize, because we didn't do this one earlier, but I do want to point this out. I think y'all already did A with Miss Estel, is that right? Miss Estel, y'all already did this A here?
Yes.
Yes.
I thought y'all did. Please, yeah. Please note here, I have the factored form graph. I have the standard form graph, but how many graphs do you see?
1.
Why is that?
They map onto each other.
They map onto each other. They're the same thing. What's the super mathy term for it? They're equivalent, right? They look different, right? This is which form? Factored form. This is? But are they the same function? Yes. Right? They map onto each other. They are equivalent functions. Madison, you focused?
Yeah.
Sure about that? Took you a long time to respond. Come on. Can't help you learn if you're not paying attention. So similar thing here with part B. I graph the factored form, I graph the standard form, and I only see how many graphs? 1. They mapped onto each other. They look different, but they are the same. They are equivalent, okay? Please note, C is what you actually just did. If you didn't already notice that. There's the factored form, standard form, and they are the same. So now we need to look at part D. All right? I want you to work on this within your small groups. I'll go ahead and tell you. We're going to come back together in just a couple minutes because I want to see what you do to start with it. There's a mistake that a lot of students make here, and it's a good mistake that we need to address. But I want you to think about it first, and we'll come back together. Don't forget, it's good, and it's okay, and it's in fact good to make mistakes. All right, work together to work on part D. Work together. You already done it? Work with each other? How could you check? Okay. If it's right, then talk to your small group. And make sure and check in with them, see if they understand.
Oh, sure.
Okay, first off, non-Punnett square is called the area model. So one thing I would recommend, but Punnett squares are what I do is I draw a square first, and then I draw the edges. Remember I showed that we're multiplying with that little symbol there? And then I showed my factor, my terms, right? Negative 3x and 2. And x, and I draw a line between x and 2. And it's just to help me organize my thoughts, right? And then I multiply. Negative 3x times x is negative 3x squared.
Then just make sure.
Negative 3x times 2
Can you
is negative
distribute,
6x.
like, could you say, oh, my x term is cubed and my
Negative 3x times that
Can you
2,
do that?
right? Because I'm literally multiplying each of these terms by each of these. 2 times that x is
Try it out.
2x. 2
Try,
times that 2
so,
is 3.
first,
And
give
then I
x
add my
plus
like terms
2 times
together.
x plus 2 times x plus 2.
Okay?
See what your
But
product of
remember,
that
you
is.
can also just distribute if you're more comfortable with it. And use that to help you organize your thoughts. Just make sure you add your like terms together, so that'd be negative 3x squared minus 4x plus 4.
Okay, this is great. Yeah, this is really good. So you have 3 by 2.
And then we'll multiply that by, and then because we've only done the first 2 now, so we multiply by 2x plus 1.
What you thought this was?
This term times another t2 term. Does that make sense?
Well, it's still fact form, but we're trying to get that standard form. My point is, you multiplied these first 2 terms already, or first 2 factors already. You still need to multiply by this third factor, so you have to do this again, but with 3 terms and 2 terms. Notice they have an example, right? So once you do 3 terms times 2 terms, you just organize it like that. But let's focus on D, try to work with that, right? And we'll come back together.
2 times x plus
X plus 2 the first time, which gives you x squared plus 2.
3 times is 0. This is supposed to be 3 times, but you've done it twice, right? So what do you need to do now? But I'm just saying, plug in another x plus 2.
So it looks like you're identifying those roots right now. One, if you're going to do that, make sure that you set it equal to 0. That's the whole point, right?
Can we do an area modification?
That we're trying to find the zeros. But that's not what I'm actually asking you to do here, right? So you can take the cube root to solve this. X plus 2 is equal to 0. And notice x equals negative 2 is a 0, but it would be with a multiplicity
Just 3
of 3, right? But what am I asking you to actually do for this problem?
something right here, right here.
That's why you
Determine
need to do
each
the
product
first
algebraically.
So you take
Remember,
2
find that
x
standard
plus
form,
You
just like we just did.
And then we be
I would suggest, it looks like AJ has some ideas going. Talk with him, and I'll come back and check on y'all in a second, okay?
The problem the problem
How do you feel about that so far?
oh, x squared times 2 is 2x. Oh, x times x,
And my question is, how do you feel about this so far? Feel confident in it? I can't help you if you say I don't know. If you have a question, what's your question?
No,
Let me ask you this, does that answer go with this graph that you have right here? So, what do you think on this?
So x cubed.
Not back to the x, but yeah, we would want to note that we my suggestion was to always write it out before I started multiplying, because that's your issue that you're running suture, because you've only multiplied 2 to x plus 2. So when you did that, you got x squared plus 4x plus 4. But you still have to multiply by another x. You actually did that. You did here, you still have to do x plus 2. Does that make sense? Okay, so let's keep it going.
I mean, I've already got that. I just.
Yeah.
You said Skylar ought to declare.
Okay. Let's just come here.
Yeah.
We've already did
I mean, how do you know they're not right?
Alright. You did the first box, right? That's how you got x squared plus 4.
How could you check to see if the answer is correct?
We never opened it.
Very nice.
Well, this answer right here. So one thing I do want to point out, be careful, that says 2x squared. Right? Do you have any like terms here that you want? Let me point this out.
So we got even closer.
What's happening between the two?
So we're going to work whenever you teach.
By the way, Tom, looks like you're a little slow. Once you, so see how they multiplied 2 here? And then they got 3x squared plus 4x minus 4. See how they took that and put it as 3 terms here and then they put the answer there. So what you would want is you would do that area model again. Just be aware that we have now x squared plus 4x plus 4. We just have 3 terms. And then that first if you do that. So x cubed plus 2x. What is multiplication right here? What is multiplication? It's a repeated something. Right. So what we really have is x squared, x cubed plus x squared plus x squared. And you add those together.
There's no way to put 3 terms on this, you can't do like x plus 2, x plus 3.
But it was 2x squared because these were literally the same thing, right? Repeated addition. Is that the same thing as x squared? Is x cubed the same thing as x squared? So then can we add them together? You can only add the terms that have the same exponent. Yes, ma'am. No, wrong spot.
So you said x equals 2.
That'd be my suggestion, yes, ma'am.
This is also true.
Why are you asking me? How can you check to see if that is correct?
It's already in the equation.
I'm not gonna be able to tell you that answer on the test, right? Check it yourself.
How do you take this equation? Right.
You don't have to.
See, if you would
Yes, right, so like, see how this is x, when you type a new equation in, it'll replace it.
So no one knows.
Can you combine this?
Yeah, you'll need.
X squared plus
That's what's up.
Yeah, it'd be x squared, on the little thing would be x squared.
You understand?
You want it?
Where's your final answer?
And I didn't
Okay,
write off
I was right
x
here.
squared.
I always write it down. And one thing I would recommend is here, I wouldn't jump straight through here to here. What I would do is
So
I
you
would
added
take
4x
the time.
right here.
Because what you originally have is x plus 2 times x plus 2 times x plus 2.
No, see,
And then you use that area to get x squared plus 4x plus 2 times x plus 2.
you tried.
I would write that stuff out. So you have your area model to find that multiplication, right? And then from here, I would do my area model again. Like you have it right, it's just taking this extra step to make sure that you can do the terms correctly. I do the opposite way. So I would recommend taking that extra step. I was saying, that's correct. How did you grab So combine your terms. No, what are you trying to do with that?
Like,
But what are you trying to do? What are you trying to do?
I like. I'm on that graph.
Use your eyeballs. What are you trying to grab? Okay, grab the function.
I just see, I
But
that's one thing I hate.
Just gonna get the shoes out, so I'll be ready to make it.
not matching up.
Okay, no, that's good, that's good. Okay, so then what goes up?
I'll say your group got a slightly different answer.
We gotta draw graph.
Because you have
Thank
one
you.
more, that's right in front.
Thank you. Thank you. Madison, you wait back there? Okay. Alright, so let's talk about this a little bit. So good news is, y'all do not make the mistake that a lot of people make. Please don't make that mistake. So I'll show you the mistake. Okay? Here is the most common mistake I see students make. What they do?
They distributed it.
That's what you
Okay.
did.
Hey, listen. Listen. So many times students distribute when you cannot. There are only two operations that you can distribute with. Anybody know what those two are? Multiplication and division. You cannot distribute with any other operations. Do not distribute that exponent. And so I'm glad most of y'all recognize that. Instead, rewrite this as x plus 2 times x plus 2 times x plus 2. Which means you're going to have to either distribute or use the area model how many times? Twice. Okay. I think everyone that I saw is good to go here. The one recommendation I will say is, I would do this extra step where we draw the full square and we show the x plus 2 and the x plus 2 in those, the row and column, the multiplication symbol here, and we get x squared, we get 2x, we get 2x, and we get 4. All right, I have my like terms there. And so what do I get when I multiply x plus 2 times x plus 2? Y'all, shh. When I multiply x plus 2 times x plus 2, what do I get? X squared
Plus 4x.
plus 4x
Plus 4.
plus 4.
Why you didn't just say what problem done when you? Okay.
I got that.
Yeah, I got it.
Okay, we good?
Yeah.
Alright. Now, I want to remind y'all, and I want y'all to slow down a little bit, write out the simplified expression, and I would also write it here to show that's what I have, but again, I'm not quite done. I don't have the full standard form. What do I still need to do?
You need to multiply the answer.
I need to distribute again. And by the way, guys, do you have to use the area model?
No.
No. If you like distributing, go for it, right? I like distributing. That's how I grew up. I did not use the area model, but I know that area model helps students organize their ideas. So if you like the area model, go with it. It does not matter, right? It'll work out correctly either way. One thing I do want to ask quickly before we continue, and I'm going through this because I did see at least one student make a mistake, and I'm sure multiple did that I just missed. But does it matter which way I set this up, do you think? No. Remember, this is just going to help me organize my ideas. So please understand, like, don't stress about which side you put it on. You just need to recognize, hey, I have 3 terms, so I either need 3 columns or 3 rows, right? Either one. And then I have 2 terms, so I either need 2 columns or 2 rows. It doesn't matter which way you set it up. But be careful and pay attention. All right, I'm going to distribute my x squared. What's x squared times x? What's x squared times 2? What is 4x times x?
4x squared.
What is 4x times 2?
8x.
Remember, there's only one x in this case, not squared here. All right, 4 times x,
4x.
and 4 times 2.
8.
Alright, I just circle my like terms, go ahead and add those together. So I start with my highest power, x cubed, plus
6x squared. Plus 12x plus 8.
Now, please hear me very clearly on this. Don't ask me, did I do it right? Because what should that be equivalent to? The x plus 2 cubed, right? And here's something I want to make very, very clear on this, all right? Let's say you did make a mistake here, and you would have the wrong answer here. You may not have time to go back and find your mistake because you might need to move on, but would it be strong evidence of your understanding if you made the note, Mr. Kinney, I graphed this and I graphed this, they're not the same, so I know I made a mistake, I just don't have time to go back and fix it. Recognize your mistakes, take the time to graph and see if they are equivalent. That is strong levels of understanding. Because if you know how to use this, could you have just made a small procedural mistake? Yes. And remember, there's a 3 plus on the scoring rubric, and you can get a 3p plus, meaning you made a small procedural mistake. And you can get to that point if you make a small procedural mistake and you still recognize, hey, I know that these aren't the same, right? Because they're not equivalent, they don't graph to be the same, right? That's a really strong score to earn those 3 pluses. So show me what you know, all right? If you make a mistake, look for it. Does that make sense about this? Where you make a mistake there? I think you added your x and 4x, didn't you? So be careful. Okay.
Pause.
What?
I'm still stuck on how you made that.
How I got what? What equation?
Oh, and Brian.
This one?
Yes.
Okay, do you understand how I got to here?
Yes.
Okay. All I did then was I took my x squared, my 4x and my 4, put it here, took the x plus 2 and put it here to be able to multiply. I multiplied and I just added my like terms. 4x squared plus 2x squared is that 6x squared, 4x plus 8x is 12x. Right? Like, it is literally exactly what we did here, except we had 3 terms instead of just 2.
So you just, the ones that didn't have a match, you just put them out?
Well, I didn't just leave it out. So I just want to clarify one thing. What you're doing with all these terms is you're adding them, right? So x cubed, there are no like terms, so I can't add anything to it.
That's what I mean. Like
But 2x squared and 4x squared, those are like terms, so I add them together.
Good job.
Quick question, because this did come up with at least one student. Does anyone know why I can't add x cubed and 6x squared? They do have different exponents, so, but why does that prevent me from being able to add them? But what does that mean to be a like term? And I think this is a fundamental thing that a lot of students miss, because I'll be honest, I don't think most teachers fully recognize this. Do not forget what's happening between this coefficient and the x squared. This is multiplication, so that's repeated. So what I really have is x cubed plus x squared being added how many times? 6 times, right? Here I have 12 x's being added, right? So don't forget that multiplication indicates I'm repeatedly adding. And I can only do that multiplication because these are exactly the same number. Are x cubed and x squared the same number? No. So can I repeatedly add? No. Okay. So that's what we mean when we say like terms. If they are not exactly the same base and power, then they're not like terms because I'm not repeatedly adding the same thing over and over and over again. All right. We do need to get to an understanding check so that you have enough time. That's going to, I guess, end the class. I didn't mean to spend that much time on it, but we'll go over the understanding check to start tomorrow. Please notice when we graph, they are the same. Please note here, we have a 0 of x equals what? What is the 0? X equals -2. Remember, it's x minus r1. With what multiplicity? It didn't touch and bounce away from the x-axis. Why not?
Because they're all
It's all power.
It's an odd power, right? It only touches and bounces away when it's
An even power.
an even power, okay? Only an even multiplicity will touch and bounce away. If it's an odd, it will always go through. We'll actually explore that more, I think, right, Ms. Estel, on Wednesday. That was a part of that lesson. Okay. Where did he talk to actually about number 3? Right? Why is Max incorrect?
We talked about 3.
Look at it.
Oh, because he didn't do it. He didn't distribute right.
Yeah, didn't Max make this mistake that we just talked about where he just distributed the exponent?
Yeah, Max, you so wrong.
X cubed,
I'm wrong.
2 cubed is 8. Max, this max right here, right? X plus 2 cubed is equivalent to this, right? He distributed that cube. You can't distribute an exponent. You can only distribute what operations? Multiplication and division. Those are the only operations you can distribute. I will also point out, how could you know that how could Max have known he made a mistake here?
He could have graphed it into the calculator.
Yeah, if he graphed it, it would have immediately told him that he had an incorrect answer.
Yeah.
This function would be shifted, or we'll talk more about transformations in the next unit. That's a translation to the left 2. This is actually a translation up 8. And so those would be very different functions. We'll talk more about translations and transformations next unit. Okay. Alright, so it's time for our understanding check. Please clear your desk. No calculators as well.
So how do you this
So how do you hold on, wait. Mr. Kennedy.
This is still there.
Mr. Kenny, do you still do tutoring? I emailed everybody about it last night, actually.
Oh, yeah. I've never
Check your emails.
Mr. Kennedy, before you get off the session, what does the bouncing to reflect the double? My brain. Yeah.
What does it bouncing off look like?
Yeah.
Hey, you just
I was asking you for that.
trying to waste that time.
Hey,
Oh,
Yo.
Lord.
I need y'all to stop talking. I need y'all to pay attention. Okay? This is something legitimately, the only new thing from last week that's on this understanding check is multiplicity, which don't make that harder than it has to be, and the multiplying. That's it. That's the only new thing off of the previous understanding check. But if I were looking at this graph, first off, where are the zeros of the dilated function?
On the x-axis. So
You asking us the number?
about -2. Where do they intersect the x-axis?
What are those points called? They're at the x-intercepts. So, you don't have to know exact values to be able to sketch this graph. I know that the dilated function has x-intercepts there, right? And I'm going to mark off my different sections here. And so, I want you to think about it. If I look at this region on the left-hand side, this is a positive times a negative times a negative. What kind of numbers are those?
Negative. That's positive,
It's gonna be positive.
Oh, that's positive, right? A negative times a negative is positive, and a positive times a positive is positive. Okay, so I know that all these values are positive going up to this x-intercept, right? That's 0. Now, I look over on this right-hand side. What is a positive times a negative times a negative?
Positive.
You see how it touches, and then it goes back to being positive? So it's going to touch and go back to being positive. It's got to hit that 0. It's got to hit that x-intercept. But I went from positive numbers back to positive numbers. And I just used that information here to help me figure that out. Now, when I look over on this side, I have a positive times a negative, which would be what kind of numbers? Okay, so I know it's going to hit a maximum. It's going to come back down to the 0. This time it's going to go through into those negatives. That's the sketch of that polynomial.
So the bouncing off would mean it wouldn't hit the 0, 0 at all. If it
Well,
was
I mean, that's the priority. The priority is never the 0, 0. The priority is that it's going to touch that 0, that x-intercept, and it's going to go back into the positives. But like you're overstressing that. You know, right, that if it's an x-intercept, it's got to touch there, right? And you know that this region is positive, right? And that this region is positive, right? So it's got to go here, it's got to touch that 0 and go back to being positive. It never goes into the negative, so it can't go below the x-axis. It touches, and then goes back into the positives, and then over here it's negative, so it goes through that x-intercept into the negatives.
Nice.
Good?
Yeah.
What?
Okay.
Okay. Alright, please erase anything that's on the desk. If there is anything there, I'm going to erase the board, and then we're going to get started.
I'm not, yeah. Can I do can I do
What? What?
That's what I'm saying.
Y'all can go ahead and get started. No, yeah, no calculators on this one. There will be a calculator portion of the test, but we're not using calculators on the understanding check. I'll come back. Hey guys, there's understanding checks out. You all need to stop talking and get to work. Please stop talking, get to work. Let's move on to a different one.